Congratulations, you did it. You made it through the AP Physics 1 2025 exam, and with that, the last of the AP exams. So you're really done now. I'm going to provide a little walkthrough here of this year's FRQ questions. So I know it's really hard to wait till July. This will be able to let you see how you did, let you see whether you cooked or were cooked. I think I'm using that right. Anyway, let's go ahead and start with problem 1. We have a student has a cart mass MC and a block 1/5 of that. At time t equals 0, the cart's moving to the right horizontally with a constant speed, and the student releases the block from rest. At a time t equals t1, the block is going to fall on top and collide, and the block does not slide. And then the block and the cart are going to coast together with some final speed v. Collisions here definitely dictate we're going to be using some sort of conservation of momentum along the way. And it starts us out by having us sketch a graph of the magnitude px, the x component of the momentum of the block cart system. So we're looking at everything together, and we're only looking at the x component. We're looking at it from a time t equals 0 all the way to t equals 1 when the block crashes into the cart, and then what they do in between as they coast together. Really, momentum in the x direction is going to be conserved here. So it's almost a trick question in a way. We pick some initial value of that momentum. If we want, we can label it mc vc to represent the initial momentum of just the cart. It's going to coast along at a constant speed. The block being dropped is accelerating, but it's being accelerated by gravity downward, so it's only changing its y momentum. The dropped block has no x momentum, and so we do not need to include it here. When the block crashes, the x momentum is still conserved for the whole system. So even though the block cart system is going to slow down a little bit, that added mass from the drop block is going to work out to keep everything the same. So we can just continue our horizontal line here going all the way across. And we're done. It's as simple as that. Momentum is conserved. If we're plotting the momentum, it's just going to be a constant value throughout the entire situation there. So that was a nice, easy way to start. Let's move on to the next part. It wants us to derive an expression for the final speed of the block cart system after t equals t2 in terms of mc, vc, and physical constants. We want to start our derivation by writing a fundamental physics principle. We said before we're looking at conservation of momentum. So that's probably the principle that we want to write, which says that the px total of the system before the collision is going to be equal to the px total after the collision. So we just need to write out explicitly what the momentums of our system are in that x direction. So before, we just have the momentum of the cart, so the mass of the cart times the initial speed of the cart. That is going to equal the total x momentum of the system after the collision, which is going to include the dropped block. And this is kind of like a perfectly inelastic collision where the objects stick together, the block doesn't slide or anything like that. And so we can treat it as a single object with the combined mass mc plus 1/5 mc. And they're moving together at the same final velocity. So all we're going to do is kind of rearrange this to solve for VF. We can add together the two masses here. We have 1/5 mc and 1 mc, which we can call 5/5 mc if we want to be a little fancy. So we get mc vc equals 6/5. That's 5 plus 1/5 mc v final. The mc's on both sides of the equation just sort of cancel out, and we're left with v final is 5/6 of the original velocity. So as a application of conservation momentum, setting the total momentum before plus the total momentum of after, that added mass here is going to decrease that final velocity, and we got that in our answer. We're 5/6 of what we started with. In part 3, it wants us to derive an expression for the change in kinetic energy of the block cart system from 0 to T2 in terms of the same variables as before. We're going to begin our derivation with a fundamental physics principle or an equation from the reference sheet. So here we're just kind of looking at the change in kinetic energy, delta K, is going to be the final kinetic energy of the system minus the original kinetic energy of the system. We can substitute in the explicit expressions for kinetic energy. The initial kinetic energy of the system is just the kinetic energy of the moving cart. So it's going to be 1/2 mcvc squared. The final kinetic energy is going to be the sum of the two objects. So we have 1/2 mcv final squared plus 1/2. The smaller block has a mass of 1/5 of what we started with. So we plug it in for the mass. And again, as we showed before, they're both moving at the same final velocity. So v final stays there. We just kind of need to simplify this expression a little bit. The half here and the 10th, or the 5, give us 1/10. The 1/2 by itself is 5/10. So we're going to get 6/10 or 3/5 mcv final squared for our final kinetic energy, and we're going to subtract from that 1/2. So we have 3/5. I guess we can put that back into tenths. So we'll get 6/10 mcv final squared minus 1/2 is 5/10 mcv final squared. We have like terms with mcv final squared on both of these. So we're just really subtracting the coefficients out front. 6/10 minus 5/10 gives us only 1/10 at the end of the day. So our kinetic energy derivation says the change in kinetic energy is 1/10 mcv final squared. Moving on to part B, it now wants us to consider the case where a new block is dropped and collides with the top of the cart. The new block slides along the cart during the collision, but does not slide off the cart. The interval where the new block collides with the cart and moves together with the cart is delta t. During delta t, there is a frictional force between the new block and the cart. Indicate whether the x component of the momentum of the new block cart system increases, decreases, or remains constant during delta t. So it's asking us, again, the x component of the momentum between the new block cart system. What's essentially happening is the block is, this is part B, not part 4. The block on top, as the cart moves forward, the block might slide backwards. As it does so, it's going to exert a frictional force between the top and the bottom cart. However, even though this new force is being exerted, and the problem's kind of tricking us by saying, oh, there's a force acting, this force is an internal force. And so we would still expect the total momentum to stay constant. We might get a different final speed for the carts. One's moving backwards relative to the other cart. But we would expect, again, this internal force would not change the momentum of the whole system, at least until the block on top falls off, which it says it doesn't really happen. So the total momentum should remain constant. There are no external forces in the x direction. All right, and that does it for problem 1. Problem 2 has a block of mass m released from rest at a position x0 is measured from, I guess, the bottom of this ramp here, along the ramp. The ramp makes an angle of theta with the horizontal. The block slides down the ramp with negligible friction at x equals 8d. So we're measuring these little increments in terms of d. After 8 of those d's, it makes contact with an uncompressed spring constant K. The spring's compressed. The block momentarily comes to rest at x equals 12D. And we're shown some important milestones along that journey here. So when the block starts at its position at the top, at 0, when it's 6D down, and when it's 10D down. Figure 4, which is down here, shows an energy bar chart representing the kinetic energy of the block, gravitational potential energy UG, and the spring potential energy US. At the point where the block is at 10D. We say that the gravitational potential energy when the spring is fully compressed is 0. So it's all spring energy at that point. It wants us to draw bar diagrams for these other positions listed above at x equals 0 and at 6D. So one thing, energy is conserved here. There are no external forces. There's no friction or anything like that would take energy out of our block spring Earth system. And so what we want to start by doing is looking at the total amount of energy listed in the bar graphs here. So our kinetic energy is a value of 7 when the block is at 10D. The gravitational potential energy is a value of 2. And then the spring potential energy has a value of 3. So if we put that all together, we have a total energy of 12E0. So if we go to when the block is at the top of the ramp, it's falling from rest, so it's not moving. There's no kinetic energy. The spring has not yet become involved. And so all we have is gravitational potential energy. That bar should have a height equal to the total energy we found over here, 12E. So I'm going to mark that on the gravitational potential energy part, and this is going to complete my bar like so. You can shade it in if you want to be fancy, but you don't have to. So that's the first one. There's no other energy except gravitational potential energy. At 6D, we should have half the energy we started with. And since we haven't yet hit the spring, all of that gravitational potential energy we started with, or I guess half the potential energy we started with, is converted into kinetic energy. So we should have both of these at 6. And we can see, 1, we're halfway down the ramp, so we have half the potential energy we started with. We can see that trend continue. When we're at 10D, which is only 2 above the 12 mark, we only had 2 units of gravitational energy. When we're 6 above the maximum compression point, we have 6 units because we're 6 away from the bottom. And here we're at the very tippy top. We've got 12 units away from the bottom. So that does that bar chart. We want to make sure that each of our bars all together add up to 12. We want to make sure if we're not moving, we have no kinetic energy. If we're not touching the spring yet and compressing it, we don't have any spring potential energy. So these are our nice bar charts. The next figure shows the block at x equals 0 when the block is released from rest, and at 12D when the block comes to rest again against the compressed spring. So starting with conservation of energy, we have a clear direction here that they outlined for us. Derive an equation for the spring constant K. Express your answer in terms of m, theta, d, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle. So our fundamental physics principle is going to be, hey, conservation of energy, exactly what they told us. At the top, according to our bar chart, we only have gravitational potential energy. So remember, conservation of energy says energy at the top is going to equal the energy at the bottom. We just have to figure out what kind of energies they are. Our bar charts already teed us up and said at the top we only have M, G, H. I'm going to write to start because that's the most familiar form of this equation. We see we're not actually allowed to have H in our question, and so we'll need a way to eliminate that later on. And then for at the bottom, we've stopped moving, we're at rest. The problem earlier said the gravitational potential energy at that bottom point is 0, so we can only ever have spring potential energy, 1/2 kx squared. We're trying to solve for we're trying to solve for k. We're not allowed to have h or x, so we need to eliminate those. And the way we're going to do that is with trigonometry. We're given the angle the ramp makes, and we're given the distance d along the ramp, and we want to find the height h that the block initially starts at. So we can write sine as sine theta equals opposite, which is h, over adjacent, which is going to be 12d. Sorry, opposite over hypotenuse. The hypotenuse is 12d from the very start to the very bottom. So h is going to be equal to 12d sine theta. And we can replace that up here. So we get 12 mgd sine theta for our left-hand side. We still have to look at the compression of the spring. Earlier in the problem, we can see that the spring starts at 8d and it goes down to 12d. So the change in position that we're looking for this potential energy equation is going to be 4d. We'll need to square that, so we get 1/2 k 4d squared. If we put this all together, we get 12 mgd sine theta equals 1/2 k. 4d is in the square. So that 4 is going to pop out and become a 16, which is going to combine with the 1/2 to give us 8 kd squared. We're solving for k. We're going to cancel out a d from each side of the equation and divide through by 8. So at the end of the day, we should get 4mg sine theta over d equals k. Sorry, it's not a 4. It's 12 over 8 is 3 halves. We're dividing both of those numbers by 4. So 12 divided by 4 is 3. 8 divided by 4 is 2. Arithmetic is difficult. It is easy to make mistakes. So that's our final answer now. So the spring constant k should be 3/2 mg sine theta over d. A good way to double check ourselves is to think about units. K has units of force per distance, newtons per meter. Up top, we have mg, which is a familiar expression for a weight force. So we have force on top divided by d, a distance on the bottom. So that units check there gives us a pretty good suggestion that we did things right, especially if we did the arithmetic right with getting 12 over 8 is 3/2. And it is. So this should be our final answer for part B. Now, we're going to interpret a graph. Figure 6 shows a graph of the energy as a function of the position of the block from 8d to 12d. The spring potential energy of the block spring Earth system is shown on the graph. On the axes shown in Figure 6, do the following. Sketch a label or line that represents the total mechanical energy from 8d to 12d. And then sketch a line that represents the gravitational potential energy, UG, for the spring block Earth system as a function of position. So remember, energy was conserved. So our part 1 here, where we're doing the total mechanical energy, should just be a horizontal line going across the top. This is kind of like the baseline for our system. And this agrees with our bar chart from earlier. When the spring is fully compressed, all of that energy should be spring potential energy. And so they match up at this point at 12D. It now wants us to draw a gravitational potential energy from 8D to 12D. So at 8D, the block is still going to go down 4. So our potential energy graph should start here. And it should go down to 0 when there is no where left for the block to fall. So we're going to continue drawing this line all the way over here, and it should be a linear decrease. From 4e to 0 across that span there. It's not asking us to draw kinetic energy. That would make up the difference. So we can see that at any given point here, the potential energy and the spring energy don't necessarily add up to 12. There still is the kinetic energy that's being dissipated or transformed into the spring energy as that spring compresses and compresses. Because the spring potential energy formula has that x squared in it, we can see that parabola here. It's going to increase pretty fast, so the kinetic energy is going to drop pretty fast to compensate for that. Finally, it asks us to indicate whether the speed v9d, when the block is at 9d, is greater than, less than, or equal to the speed of the block when it is at 8d. And the answer should be, the speed should be less. It wants us to justify that using energy lines or curves we drew in part C. And so if we go back to our graph here, at 8d, the kinetic energy has to make up the difference between the 4 and the 12. So there's no spring energy yet. That means that at this point, the Ke has to be equal to 8E0. At 9d, we have a combination of potential energy at about 3 and just a little less than 1 here for the spring potential energy. So together, that gives us 3 plus 1. Oh, maybe it's the same. See, this is why we always check our work. I mean, it's a little less than 1 there. So the spring potential energy crosses just below 1. So we actually have 3 for gravitational potential energy plus a little less than 1. So we're at like total potential energy at like 3.9, which means we need a full 8.1 energy in kinetic to make up to the 12. So actually, if we're interpreting this as the potential energy being at 3 and this spring energy being less than 1, the kinetic energy actually increased in that time. And so my initial thought was incorrect. We should go back to V at 9 is greater than V at 8. Essentially, we used our graph to justify that. We said that total energy always needs to be 12. E0 at 8d, we have 0 spring potential energy and 4 gravitational potential energy. And at 9d, our spring potential energy is like 0.9-ish. And our gravitational potential energy is down to only 3 units. So here our leftovers are 8 for kinetic energy. Here our leftovers are like 8.1 for kinetic energy. So we actually do have more kinetic energy and therefore more speed. More Ke goes to more speed. So that is definitely an unintuitive one. Moral of the story there is 1, trust your graphs, trust what you did on your graph and interpret that graph especially, and then don't be afraid to change your answer if you do find something in your analysis. My instinct was that the speed should have decreased, but the graph said the combination of that spring and gravity working together means that the speed actually increases. So that's a tricky one, definitely. And that ends problem 2. Well, looks like we've got some torques. Students are investigating balancing systems using the setup below. Students have a spring scale of negligible mass fixed to one end of a uniform meter stick. The center of the meter stick is attached to a stand on which the meter stick can pivot. There's a hook of negligible mass fixed to the top of mass M0. The hook can be attached to the meter stick through one of the small holes on this side of the stick. The students don't have a direct way to measure the mass of the block, and the block cannot be attached to the spring scale. It's an awful lot of restrictions, but we'll play their game here. The students want to do an experiment or take measurements that will let them find M0 of the block. We want to determine an experimental procedure to collect data that would allow them to determine M0, include any steps necessary to reduce experimental uncertainty. And we're going to describe how we could collect that data in part B. So I suppose our strategy here is to balance the torques, measuring the spring scale, measuring the resulting force on the spring scale. So what we would probably do here is place the mass 0 at the 60 centimeter mark, and then hold the spring scale and record the force measurement when the system's in equilibrium. So we're going to put the mass on at that slot. We're going to let the spring scale stretch out to keep the system balanced. And then we're going to record the force on the spring scale that makes that so. Then we're going to move the mass to the 70 centimeter slot and repeat the above steps. And then do this again for the 80 and 90 centimeter slots. So we're basically, our independent variable here is where we're placing the mass from the center of the meter stick, and then the dependent variable is going to be the force reading on the spring scale. Lastly, after we've gotten all of our data, we're going to repeat this a bunch of times to reduce error. Multiple trials. I always tell my students you should be, even if you have no idea how to do a lab design problem, you should always you're going to do multiple trials. It's free points. They want to know that you know how to reduce error. The best way to do that is to do it multiple times. Doesn't matter, 3 times is, average, probably realistically what you would do in your actual lab periods, but, you don't actually have to do the experiments here, play their own game against them and say you're going to do it 100 times, 1,000 times. Go for it. So this is our experimental procedure. How are we going to analyze this data? Well, we are going to compare torques. So this is part B, we're going to balance the torques. The center of mass at the meter stick's right at the center. If we choose that as our pivot point, it's not going to exert a torque. So we're really just looking at the force on the left side that we read on the spring scale. It's going to be a distance of half a meter away from the center. And then we're going to look at M0G is the force that the weight of the mass exerts at a distance x. And again, x is our independent variable where we are placing it from the center. So we'll have data points for, 0.1 meters, 0.2 meters, 3, and 0.4 meters in our data table. So we're going to have the force measured on the scale versus, if we divide both sides by a half, we're going to get 2m0gx. So we're going to plot the force on spring scale versus the position of the mass. This is going to be a linear relationship already. And so the slope of that relationship, again, this is our y variable. That's the dependent variable. x is x. That's our independent variable. So we have like a y equals m as a slope x. Maybe there's a plus b, but we don't really care about that here. 2mg is the slope. G is 9.8 meters per second squared, as is usual, the acceleration from gravity. And so once we have our slope, we can divide the slope value by 2g, and that will be equal to the mass, the unknown mass we're trying to find. So we took our experiment, we plotted the two values against each other, and then we interpreted the slope by balancing the torques as a way to extract that unknown mass from that data. I guess there's text here we should probably read. It's kind of poor formatting on their part. The students have an identical meter stick of mass m that's now attached to an axle fixed to a wall. The meter stick's free to rotate with negligible friction about that axle. The meter stick suspended horizontally by a string connected to a spring scale of negligible mass, as shown in figure 2. So we've got now the meter stick is being held up by a string. The angle theta that the string makes with the meter stick can be varied by attaching the string to one of the pegs along the wall. So where we attached the masses before, now we're just kind of connecting a string and it's suspending it from above. I guess we could change it down here, but they're saying they're changing the angle by changing where it attaches to the wall. Students measure the force in the spring scale, which is the tension in the cable, as a function of the angle that the string makes with the horizontal. So this page is just kind of setting things up. Eventually, they asked the students correctly determine that the relationship between the tension and theta is given by 5mg over 6 sine theta, and they want to create a graph with 1 over sine theta plotted on the horizontal axis. So they already give you the linearization. You don't have to think about it, really. You just have to kind of do what they say. So they say, indicate what measured or calculated quantity could be plotted on the vertical axis to yield a linear graph that would allow them to determine the mass of the meter stick. Well, the equation that they have here, we already have a data table that has an angle, an ft. They're going to plot 1 over sine theta. And so it tells us on the horizontal axis, they're going to do 1 over sine theta. On the vertical axis, we're going to plot ft, which we have from the data. Now, it's worth noting that, 1 over sine theta, if we were just to plot theta, for example, that would be definitely a nonlinear graph. However, plotting this whole function does turn this into a nice straight line. So they want us to do 1 over sine theta. We'll probably need to calculate what that value is. So this will be 1 over sine theta for each of our 5 data points here. So if we put those values into our calculator, we get 2.67, 1.94, 1.70, 1.41, and 1.06, which seems to match well with the values they already have on their scale. They kind of took a lot of the fun out of doing this problem. Like, you don't even have to do the scale yourself, but maybe that's a good thing. Probably in your perspective, it's a good thing. So these values fit definitely in the scale. We do have to pick a y scaling for the force of tension. So our force of tension, I want to make sure we label that, and it is in newtons. We need units. The values for force of tension go from 0 to 21. They give us 1, 2, 3, 4, 5 boxes. So maybe let's go up in terms of fives. So we get 5, 10, 15, 20, and 25. That way we're using the whole space they give us and we're incrementing it in nice, reasonable amounts. So now we're just going to plot our values at 1.06. So these are increments of 0.1. So somewhere a little bit in between the first and second tick mark after the 1. we're going to go up to a force of tension of 8 newtons. So our increments on the y-axis are just 1. So we go 5, 6, 7, 8. We're going to go there for our first data point. The next one's at 1.41 and 12. So we go basically right on the 1.4 mark. There at 12. We have 1.7 and 13. So that's there. We have 1.94 and 17. So about here. And then finally 2.67 and 21. So we jump all the way to 2.67, take about the 2.7 mark, go a little before that, and go to 21. So probably right around here. And we have some data that looks approximately linear. To do that, we want to find a nice line of best fit. Pass through the data. You want to generally have an equal number of points above and below your line. So it looks like I might be able to kind of center my straight edge on that largest point there and kind of have it pass right through the rest of my data. They're going to have a little bit of leeway as long as you're matching the trend of the graph. So there doesn't have to be an exact line. If you're familiar with doing regression in your calculator, you can definitely do that, but you'll want to tell them that you did regression. You have to make sure that you said, I got this answer from regression. And it kind of tells them that you know what you did. So we get a nice line. We have 2 lines below, 2 dots above, and 1 point right on the line, and this would be a good enough line of best fit for this data. It wants us to use the line of best fit to calculate an experimental value for the mass of the meter stick. So now we want to pick 2 points actually on our line. You can pretend like the data doesn't even exist at this point, really. And I like to pick lines that are, on definite grid line intersection. So there's a good one there and a good one there. So we take our y values. It looks like I have 16 and 12 for those. And then my x values are 2 and 1.5. Those are nice round values. So 16 minus 12 is 4. 2 minus 1.5 is 0.5. So I have 4 divided by a half, which gives me a slope of 8. We're going to go back to the equation that they use to model this thing. If we're plotting ft versus 1 over sine theta, our slope, 8, is going to be equal to 5/6 mg. So now if we solve this expression for m, noting that g is 9.8, we'll get 48 over 5 divided by 9.8 equals the mass. And if you plug those values into the calculator, you'll get something about 0.98 kilograms. So just under a kilogram, almost exactly a kilogram. Again, depending on how you drew your line, you're just doing it by hand, you're eyeballing it. There's going to be a range of values. If you get something probably between 0.9 and 1 point something, they'll give you full credit there. So just make sure that your line is nice and straight. You're taking data points off the line and not just blindly off the data chart. For example, if you just pick these 2 points, you get a very different line of best fit than the one that we drew that captures all of our data. So you'll be in good shape there. And that ends the dreaded lab design question. We're almost there. One more to go. And it looks like from this diver here, it's a fluids question. We have a swimmer holding a block of mass m in a tank of fresh water with density rho 1. The block's released from rest and accelerates upward with initial acceleration a1. All frictional forces, drag, and whatnot are negligible. In scenario 2, the swimmer holds the same block in a tank of salt water where the density rho 2 is greater than rho 1. Releases the block from rest, and the block accelerates upward with the initial acceleration a2. All friction forces are negligible. says indicate whether A1 is greater than, less than, or equal to A2 by writing one of the following in your answer booklet. Is it greater, equal, less than, or equal to A2? We're going to say that A1 is less than A2. Justify your answer in terms of all of the forces exerted on the block in each scenario. Use reasoning beyond referencing equations. And so what we're going to talk about is the forces on the block. I'm surprised I don't have you drawing an actual force diagram. That would help to do on the side, maybe. The forces on the block are the buoyant force upward and the weight of the block down. The buoyant force depends on the density of the fluid. Depends on fluid density. And so, since the salt water has a greater density, there will be more force upward, but the same force due to weight. This means the net force is even greater upwards and will accelerate upwards more. A upwards is thus more. In part 2, they actually want us to derive an equation for the initial upward acceleration of the block when it's released from rest. Our answer can be in terms of the mass, the volume, and rho, as well as physical constants. So we're going to start referencing Newton's second law, which is, F net equals ma. The net force is going to be that buoyant force upwards minus the weight of the block downwards. So now we need to write these things in terms of the given variables. The buoyant force is going to be the fluid density, rho, the volume of the block, v. Everything's fully submerged, so we just get to use the full volume, and g. In other words, this is the weight of the fluid displaced by the block. Rho v gives you the mass of that fluid there. And then we're going to subtract from that the mass of the block, m, times g for the usual weight force. This is all equal to ma. And well, it's nice. I've substituted these things in. Everything is in terms of rho I'm allowed to have. V I'm allowed to have. G is a physical constant, so we're allowed to have that. And the mass of the block is something else we're allowed to have. So now all I will need to do is just solve for A. Divide both sides by m, and I get A is equal to rho Vg over m minus g. If we're not sure, again, this might be an unfamiliar formula. It needs to have units of acceleration. G has units of acceleration by itself, so this kind of term over here by itself is good. Rho v is a mass. Remember, density is a mass per volume. So if I multiply a density by volume, I get a mass. Divided by another mass cancels out, and we get g, which is acceleration. So this hints that we've done things right, and this is a valid formula for acceleration. Finally, this is the last part of the whole thing. See, it says stop, end of exam. We're almost there. We're going to indicate whether the expression for the acceleration is consistent with our claim in part A. So we just need to interpret our equation. We said in part A, greater density is going to give you more acceleration upwards. Does our equation over here say that? Yes. A and rho are directly related. If I make the density of my fluid larger, that's going to make this front term larger. Subtracting g is going to affect it less, and therefore A will go up. So yes, more A, we'll say A and rho are directly correlated. So increasing rho increases A. Boom. That's all we have to say. If something went wrong in part 2 and you got something really weird where maybe A was like, you just jumbled up the algebra or something like this, and this was your final answer. Maybe you don't see that. This is the last question. You're pressed for time. You need to write something down. Well, if I got this, maybe it wasn't the right answer for part two. I'm going to lose those points, but I can still get full credit for part three. All I need to note is, in this wrong equation, A and rho are inversely correlated. So, I'm going to just say what I see here. If rho goes up, A should go down, and therefore the acceleration would be less. It does not agree. So if you got part B wrong and you wrote something like this, stick with your guns. Say, no, this doesn't agree. As rho goes up, A goes down. And then they see that you interpret what an equation like this looks like, and that you still get the benefit of the doubt for part three. So there you go. That's the entire AP Physics 1 FRQ. If you think I've made a mistake, I was kind of looking at these blindly as we went. Tell me about it in the comments. We can have a discussion of what the best way to go about this was. In any case, I hope this was useful to you. Hopefully you can get some rest now that you know how well you did on the AP exam. And I hope there are many 4s and 5s in your future. Congratulations again.